All right, team. So 2 sets of notes for today. First set of notes is going to be on polarity, and then the second set of notes is going to be on attractive forces. Something to keep in mind when we are thinking about, let me start with a piece of paper. Okay. So you guys would have done polarity of molecules last year in structure and bonding, and something that I wanted you guys to keep in mind with the general structure of how we answer this question is the first thing we need to think about is, do I have polar bonds? I'm sorry, let me backtrack. When we talk about polarity, unfortunately, we use the same word for 2 different situations, and we need to be careful about when we use each word. So the first off is polarity in reference to bonds, and the second one is polarity in reference to molecules. So just as a refresher of how we structured our justifications, the first thing we looked about when we were justifying, justifying polarity of molecules. So basically what we're thinking about when we're trying to justify the polarity of molecules is we're trying to say, is it charged or is it uncharged? That's what we're looking at. And when I say charged, I wouldn't even say charged is the right word. I would say slightly charged. So it's a region that is slightly negative and slightly positive, whereas a nonpolar molecule will have either the charges will cancel out or there's no charges to begin with. When we're coming to justify this, there's several different layers we need to use, and just as a refresher for you guys, and then I'll show you guys the bits and pieces. The first thing we need to think about when we're looking at justifying if a molecule is polar is we need to think, are there polar bonds? And that's going to tie into the concept of electron negativity. Sorry, not spelling it right. And then the second thing we need to think about is the symmetry of the molecule. Sorry, I should backtrack. Are there polar bonds? This is going to have to deal with electron negativity. When we look at these 2 things, obviously, then that's going to tie into, do we have an unequal distribution of charge? My God, what's going on today? Unequal distribution of charge is our first question. If the answer is yes, then we continue down on the pathway. If the answer is no, then that's really easy. I have a nonpolar molecule. So the first thing I need in order for a polar molecule to exist is polar bonds. So if there's no polar bonds there, I can automatically put it into the nonpolar category. The next question I need to ask is, okay, what is the symmetry of the molecule? Now, the reason why I ask this question is I want to basically see, does the regions of electron density, or sorry, does the charges, the slight positive or slight negative and things like that, do they cancel out? Is our next question. If it's yes, actually, let me backtrack. If it's yes, then it goes to, it's a nonpolar molecule. And if the answer is no, then it is a polar molecule. So those are the layers we're thinking about when we're justifying our answer. And I'll go through and break down each one individually just so you guys are aware of what we're looking at. But that was the overarching idea of what we're looking at and what we're thinking about. Are we okay so far? All right, I still see some pens going, so I'll give you guys a second just to write. And let me know if you can't read anything, because I know I do write fast and get sloppy when I do that. I like to think of this as a flow chart. Not, I think thinking of it as a flow chart will help you structure your answers. It'll also, what's the other thing? It also shows you the process of how we decide the polarity of a molecule. All right, can I move it now? Cool. Esther, are we good? One more second. Okay. All right. So I'll backtrack and I'll first talk about, are there polar bonds as our first kind of thought process. Because you do need to be mindful that even though these are just very short questions, you do need to justify your decision in that. Cool. All right. Here you go. Becky, I'll give this to you in case you're still writing. So we're looking at this first question here. There you go. Lots of that. Okay, so the first thing we're thinking about is, do I have a presence of a polar bond? Because that's going to be the first deciding factor. So what I've done is I found this image here that communicates the difference between covalent bonds and ionic bonds. And then when we think about covalent bonds, what the difference between polar and nonpolar is. So the main difference, first off, when we're thinking about the difference between a covalent and ionic bond, is that an ionic bond, the electron gets transferred from one atom to another, forming ions. And then the bond that's forming between these two things is the result of electrostatic attraction. We have something that's very positive and something that's very negative, and opposites attract, and that's what's causing the ionic bond to form. The next type of bond that we have is a covalent bond, and that is when the electrons are getting shared between two atoms. This is a stronger bond compared to the ionic bond. So when we see covalent bonds, it's going to take quite a bit of energy to break them apart. The other thing to think about with these covalent bonds is, where are these electrons that are being shared? So we talked about Lewis structures on Friday, and we talked about how we had bonded and unbonded, and when they're bonded, they're being shared between two electrons to make up enough to then get stable. When they are doing that sharing, sometimes that sharing occurs unevenly, where one of the two atoms pulls the electron slightly closer to it. It doesn't pull it close enough that it results in the transfer of electrons, though. They're still both sharing it. It's just, in the game of tug of war, it's being pulled to one side more. If we have a non-polar covalent bond, then those are being shared equally between our two atoms. Are we okay with that so far? Now, the way we decide this is by thinking about things as a continuum. So I don't want you guys to think about it necessarily as like categories. It's like a spectrum of what's happening. So what we look at is, we look at the electronegativity differences between the two atoms that are involved in that bond. So that's the electronegativities that we talked about here. Remember, you won't be given the electronegativities on the exam. Do not memorize them, though. It's not a very useful thing to write in your answer, being like, oxygen has electron negativity of 3.5, whereas nitrogen has an electron negativity of 3. The difference is 0.5, and so therefore it's going to be this type of bond. That's not a good use of your time. Okay? You just need to know roughly polar, nonpolar, ionic. So depending on the difference in the electronegativities, you're going to get different bonds. If the difference between the two atoms is very significant and is greater than 1.8, you then have an ionic bond. This only really occurs, or this, I should say, only occurs when you're dealing with something from the metal side of the periodic table and the non-metal side of the periodic table. That's when the difference is going to be great enough. So again, do not memorize these numbers. Just have a general reference point in your head that taking that and that's going to result in a difference that's going to result in an ionic bond. All right. The next one to then think about is the polar and the nonpolar. Again, it's about 0.4. Don't need to memorize that either. Just go think about it like the two atoms involved in the bond must be very similar electronegativities. Really, really close. So even the hydrogen-carbon bond is, on the edge of nonpolar. So what that basically means to you guys is that the vast majority of the nonpolar elements being bonded together are going to form a are going to form a polar bond in some sense. All right. That's something else to keep in mind. Like I said, don't memorize all these little numbers. It's not going to be terribly useful, but just know for most things, it's going to form a polar bond. Like even carbon with nitrogen or carbon with oxygen, you are now getting into the territory of polar covalent bond, because it's just 0.4. 0.4 is a very small number. Mostly when we're talking about nonpolar things, we're going to be talking about things that are basically two of the same atoms. So if I had chlorine and chlorine, it's 3 minus 3, that's obviously going to be 0, so that's going to be a nonpolar bond. So those are things to keep in mind. Most of the molecules you will be given will have a polar bond because of just statistically speaking, they're very likely to have a number greater than 0.4 but less than 1.8. Because if it's 1.8, you're going to deal with a metal and non-metal. Are we okay with that? All right, so think of it, like I said, as a continuum. This is a useful website. I'll link this onto my Google site. It's a good way to kind of just like help you decide whether or not you're going to get a polar or, sorry, if you're going to get a covalent bond or an ionic bond. So for example, if I did nitrogen and then fluorine, I look at those two. Well, electron negativity wise, these are very opposite. They should form an ionic bond. And then ratio wise, I need 1 and 1. And you see, it's going to show you that it's transferred like that. So it's a good way to test you if you're not sure about identification. If we reset this page and I go, let's say oxygen, and it's going to only let me do chlorine. I look at these two things here. These two things are going to be forming a covalent bond. And when I think about the atom numbers that I need, oxygen has 2 spaces, chlorine only has 1 space. So I should need 1 oxygen and 2 chlorines. And it'll actually draw the Lewis structure for you. So it's a good way to kind of get a rough idea of what you're doing, covalent or ionic bond-wise. And look, it's even giving you the shape. Are we okay so far with that? All right, so like I said, most things you're going to deal with are going to have polar bonds, just because statistically it's likely to happen. All right, so that answers our first question there. So just be mindful that when you are talking about like electron negativity and polar and nonpolar bonds, you should be comparing the two elements against each other. Which one's more electron negative? Which one's going to be more likely to have the slight negative charge? So for example, if I was trying to deal like carbon and oxygen as an example, and I'm trying to think, okay, look at the periodic table, which one should be more electron negative? We do know from the patterns that we are aware of is that as we go up and across, they get more electron negative. So when I look at carbon versus oxygen, even without the numbers, carbon I know is more electron negative than oxygen. So if I'm thinking about this logically, the electrons will get pulled closer to the oxygen and they get pulled slightly away from the carbon, making it slightly positive. So this is the slightly positive end, that's the slightly negative end. And we use that little delta symbol to indicate that that's only very minorly negative. It's not full negative, it's not full positive, because those are then ions. So when you are just finding the answer, make sure you're referring to the two atoms involved in the bond and which one is the more electron negative one. Because then we can use that to build the rest of our answer. Are we okay with that so far? All right, the next thing we need to then think about, so this should be a yes or no answer. It's very unlikely you're going to be given something that is nonpolar bond-wise. So you're going to have to go to that next question. Is it symmetrical as a molecule? And that's when our shapes start coming in, which is why I gave you guys your shape ones if you weren't here on Friday. You're looking at these guys over here. All right, so what we're looking for in this case is symmetry. And basically what I'm trying to see is, do my regions of electron densities cancel out? One thing to keep in mind as an important factor is if I have a lone pair of electrons, definitely going to be a polar molecule, because those lone pairs of electrons are going to result in an unequal distribution of charge, because even though it's negative, the lone pairs of electrons are slightly more negative than a slightly negative atom. So if I was looking at this square planar shape here, even if I have electron negative elements on the end, the negativity of the lone pairs of electrons is greater than the negativity of an atom that is slightly negative. So that's automatically going to make it unsymmetrical. Are we okay with that? So if you're seeing anything with lone pairs, you're likely dealing with something that's going to be polar. So when I'm looking at things like this, like the octahedral or the triagonal bipyramid, what I want to look for then is I want to see all the atoms involved in that bond, and I'm looking for symmetry. They like to do really easy, obvious questions. Basically, you're going to be comparing something that has all the same atoms versus something that doesn't have the same atoms. And let me pull up some of the questions now so we can see what they look like. I want it off my No Brain Too Small. That's shapes. Oh, the shapes and polarity. Sorry, I should have said that's shapes and polarity. Make this bigger. Whoops. All right. So here's the first molecule that they've already given you. What you can see here is you have chlorine, chlorine, fluorine, fluorine. And what you're looking for is symmetry in the molecule. Now, yes, chlorine and fluorine are all electron negative elements, and they're going to pull the negative charge outwards. But the problem is fluorine is more electron negative than chlorine. So even though, yes, all of it's negative, these sections are a little bit more negative than the chlorine. So that then means we're not going to get symmetry. So this would then result in a polar molecule. And that's hopefully correct. Let's double check. On the bottom. Polar molecule. So again, be really careful. So it's like, yes, both of these are going to are more electronegative than phosphorus. So both are going to result in polar covalent bonds. However, even though the dipoles are arranged symmetrically, fluorine is a different electronegativity than chlorine. And so there's going to be different strengths in that dipole, resulting in it not canceling out. Therefore, it's a polar molecule. All right? So just making sure you're getting the layers. The other thing that you have to be really mindful of is you have to be careful in making sure you're referring to each component. So that's why I'm saying you have to go back to talking about the two atoms involved in the bond. And if there's multiple types of bonds occurring, you need to talk about each type of bond that's occurring. Let me find you another one so you guys can get a C of it. So this one here and here, both of these, they want you to compare and contrast the shapes and the polarities. In this case, they both have the same things being bonded together. It's the fluorine to, I don't know what AS is actually. So this one, though, is symmetrical. So this one's going to be a nonpolar molecule because you see how it's fluorine, 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 fluorine. There's no lone pairs. All that's going to cancel out. So that's nonpolar. Because for a polar molecule to occur, it needs to have an unequal distribution of charge, and that charge needs to be like different types of charges. It can't all be negative. If it's all negative, then there's no difference. This one here, again, it's negative, 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 and negative, but the lone pairs of electrons has a slightly different amount of negativity than the fluorine. So this one's going to be a polar molecule. All right. This is what I'm saying is what is easier about thermo versus organic. There's stuff like this you can take a guess on. You don't have to actually understand what's going on. So for questions like this, just take a guess on polar or nonpolar. You have a 50-50 chance of getting it right, and it's very likely that both of them will be one of each. They won't give you two polar, they won't give you two nonpolar, because they want to be able to compare and contrast. So take a guess on the polarity, take a guess on the shapes, because often they are, and they cheat points for those guesses. All right? So that's what we're looking at for that. Any questions, concerns, or comments? All right, I'll leave you to that for now. I'm mindful of the time. I might have to do the second set of notes already. We're ending at 10 past, aren't we? Yeah, okay. Cool. Let's talk about the other ones. Okay, we're done with these. Let's open up that. All right. The thing is, these two, as much as I don't want to put these two lessons together, it's actually not the end of the world. They're not too difficult conceptually to understand, I don't think. All right. Cool. Okay. So that's that notes. I'll pause the video and I'll start a new one because I'm mindful of our time.